Okay, so here we were in the middle of this example, and so far what we've done is we've come up with a way of determining a basis for the column space of this matrix A, and you decided that the first three columns constituted a basis because when you performed row reduction on this matrix you found out that those were the pivot columns of the matrix. Therefore, if we get rid of column number 4, then any vector equation predicated on linear combinations of the first three vectors will have a unique solution because each column will have a pivot. And therefore, those first three columns are linearly independent because their homogeneous equation will have a unique solution. So now we're moving forward and talking about the null space of this matrix instead. And the null space is the set of all vectors that A kills, in other words, sends to the 0 vector. And we found an example of a vector W that belongs to the null space, and we only found that example, though, because it was handed to us. That the vector 2202, we found out A actually kills it. So if we want to go further and answer the question, well, okay, this vector belongs to the null space, but what other vectors also belong to the null space? What else does A kill besides 2202? Let's figure out how to answer that question. So again, what is the null space of A? The null space of A is the set of all solutions of its homogeneous equation. It's the set of all x such that A times x is equal to the 0 vector. So to answer this question, we need to just come up with a solution, solve this system. So yet again, our tool is row reduction. What we'd like is we'd like to solve the equation AX equals 0, so the matrix equation having zeros on the right-hand side. Luckily for all of us, though, you've done the row operations that are necessary to bring the left-hand side into its row echelon form. You did that in your previous problem when we were trying to figure things out. So the first row was
1, 0, row 1, 1.
okay.
Sorry,
Yes, sorry.
0,
Negative 2.
0, 1, 1, negative 1.
0, 1, 1, negative 1.
And then 0, 0, 1, 0.
Okay.
0, 0, 16, 0.
And then I would say we could actually do one more row operation. Let's subtract 16 times row 3 from row 4, and it'll zero out that one right there. Because again, we couldn't say that that 1 is a pivot unless it had only a 0 underneath it. So here was the row echelon form of your matrix when you row reduced it. But if we were solving the homogeneous equation, what's going to be on the right-hand side in this augmented matrix? Zeros. After all, there is no elementary row operation that's going to change a column of all zeros. That's the nice thing about the homogeneous equation. So if I want to know what is the solution of this homogeneous equation in parametric vector form, I should probably take this a little further, right? Let's take it all the way down to reduced row echelon form by trying to clear out the column above each of the pivots. So to clear that out, we'll do row 2 minus row 3. And then once that's been cleared out, we're also going to do row 1 minus the new row 2. Will be our very last step. Minus the new row 2. So we'll do those couple of steps. So here's our reduced row echelon form. Now all of our pivots are alone in their column and in their row. And so how do we find the solution of this homogeneous equation in its parametric vector form? Yeah, let's write the parametric vector form by converting this from a matrix back into equations with variables in them. So our first equation would read something like x1 minus x4 is equal to 0. Second equation would read x2 minus x4 is equal to 0. Our third equation would read x3 equals 0. And what's our fourth equation telling us? Well, not much, right? 0 equals 0. So instead, what do we say about x4? x4 is free. After all, that was the column that didn't have a pivot. So x4 is free. So I'm just going to write that as x4 is equal to x4.
So x1 and x2 are equal to each other also?
Yeah, x1 and x2 would be equal in turn to x4, just moving that x4 to the other side of these equations. And to get our parametric vector form, we'll just replace our free variables with meaningless parameters. So instead of calling x4 x4, I'll call it t. And if I call x4 t, that means I have to call the other x4s that I see here also t.
So you would have x1, x2, x3, x4 equals,
Yeah, let's get the vector part of this in here. We'll just make this into a vector and this into a vector. If we do that, we only need to write one equal sign. And now factor the t out of this vector. And that gives us the parametric vector form in a very explicit way. So there's the parametric vector form of the solutions of the homogeneous equation, where x here is this vector x1, x2, x3, x4. So what we're saying is that the null space of A, in other words, the solutions to AX equals 0, consists of exactly those vectors x such that x is equal to t times 1, 1, 0, 1. What is the basis of that set? If I unpack this equal sign here, I can rewrite this as x is any multiple times that vector, 1, 1, 0, 1. Which means, since there's only one vector here, we could equally well say x is any linear combination of the vector 1, 1, 0, 1. And if this set consists of all linear combinations of 1, 1, 0, 1, that must mean that this set is the span of 1, 1, 0, 1. So what is the basis for the null space of A? 1, 1, 0, 1. The set consisting of the vector 1, 1, 0, 1. Because any solution of the homogeneous equation, AX equals 0, can be written as a linear combination, i.e. a multiple, because there's only one vector here, of the vector 1, 1, 0, 1. So to find a basis for the null space of a matrix, we've got to solve that homogeneous equation. But when you solve that homogeneous equation and place your solution into parametric vector form, the basis pops right out at you. It's the vectors that are being multiplied by your free variables, your free parameters, to describe your parametric vector solution. So being a 4x4 matrix, A represents a linear transformation from a 4-dimensional space into a 4-dimensional space. And since the app that we usually use illustrates 2 dimensions to 2 dimensions, we're just going to draw our own picture here. That the domain is 4-dimensional and the codomain is 4-dimensional. And what we found out was, first of all, that the first 3 columns of the matrix A form a basis for the column space. So these 3 vectors were a basis for the column space of A. And because they're a basis for the column space of A, those are vectors that live in the codomain. Because they're all B's. The column space of A is a set of B's such that B is equal to AX, right? Such that the solution, the system AX equals B is consistent. And so the span of these three vectors over here in my codomain if I take the span, the set of all their linear combinations, I get the column space of A. On the other hand, in the second part, we found a basis for the null space of A. And notice that that basis for the null space of A did not come out of the columns of our matrix. And the reason it didn't come out of the columns is that these null space vectors don't live in the codomain, they live in the domain, because they are vectors that they're vectors that A kills, that it sends to 0. And we found out there was only one, and it was the vector 1, 1, 0, 1. So in other words, there was one vector back here, 1, 1, 0, 1, that when we apply A to it, when we hit this vector with the matrix A killed it. It sent it to 0. And so the null space is the set of all of its linear combinations, but because it was just one vector, the set of all of its linear combinations was just a line back here. So that's the null space of A, is that line. And so this is kind of a picture of what's going on. But now I've got to ask you this. What relationship exists between the number of vectors that it took to describe a basis for the column space? So how many vectors did it take to give us a basis for the column space of A? In this example, there were 3 vectors. And the number of vectors that it took to describe a basis for the null space. The number of vectors there were in the basis for a null space of our matrix, well, there was just this one. Why is that not surprising? So how could I have known already, after I found the basis for the column space of A to be the first 3 columns of this matrix? We did that by row reducing. How could I already have known that there would only be one vector in a basis for the null space? In other words, how does this tell me not which vector belongs to the basis, but how many vectors will belong to the basis? Why is there only one vector in a basis for the null space of A here? It's got a lot to do with the free variables. What exactly does it have to do with the free variables? Where did this 1, 1, 0, 1 come from? If we rewind the tape a little bit, back to where we solved this system, blah, 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 blah. There was one vector in our basis because when we solved the homogeneous equation, AX equals 0, we got a parametric vector solution that had how many parameters in it? Just the one, t. And since our parametric vector solution had only one parameter, there was only one vector in a basis for the solution set, i.e., a basis for the null space. So we had one parameter in our parametric vector solution, which meant one vector in our basis, and we had that because, as Alex said, we had one free variable. And backing that up yet one more step, we had one free variable because we had what in our original matrix? Where do the free variables come from? Yeah. It came from a non-pivot column. So hanging on to that observation, let's go back to the question that we were asking here. How could we have known right away that there was only one vector in a basis for the null space of A?
The fourth column.
The fourth column, there was one non-pivot column. So that one non-pivot column explains why the null space is one-dimensional. The three pivot columns explain why the column space is three-dimensional. I'm using the word dimension here. Dimension is just another word for the number of vectors in a basis. So to reframe what we said here, the dimension of the column space of A, that was the number of vectors in its basis, and since its basis had those three vectors up here in it, the dimension of the column space of A was 3. And likewise, the dimension of the null space of A, that was the number of vectors in its basis. Sorry. That's 1. So now tell me, what relationship therefore must always exist between the dimension of the column space on the one hand and the dimension of the null space on the other hand? Given where they come from. Exactly. They must add up to the total number of columns in the matrix. Because every pivot column became a basis vector in the column space, and every non-pivot column became a free variable which contributed to a basis vector for the null space. And since every column either has a pivot or doesn't, that means every column either contributes to the dimension of the column space or to the dimension of the null space. And those two dimensions, therefore, must add up to the total number of columns in our matrix. That's a theorem. And to coin the name of the theorem, all we'll do is add one more pair of vocabulary words to your vocabulary for today. Namely, that the dimension of the column space of a matrix is called the rank of that matrix. So that's a definition. Rank just means dimension of column space. And likewise, the dimension of the null space of a matrix is called its nullity. By definition. So rank is dimension of column space, nullity is dimension of null space. And the theorem that we have just justified in this specific example, but there's no reason for it not to be true in the more general case, is that, and let's write this in generality now, if A is a matrix with m rows and n columns, then the rank of A plus the nullity of A has to equal what? The number of columns. Right. And here the number of columns is n. And that's a theorem that we call the rank plus nullity theorem. It gives a relationship between the column space of a matrix and the null space of a matrix based on their dimension. The dimension of the column space and the dimension of the null space have to add up to the total number of columns in our matrix. Because again, every pivot column contributes a dimension to the rank, and every non-pivot column contributes a dimension to the nullity. And every column has to be one or the other.